AP Chemistry, we are in Unit 6 of Intermolecular Forces. This is a topic that's tested pretty heavily on the AP exam. We're in Lesson 2. We learned the 4 different types of intermolecular forces in the last lesson, and now we're going to learn some of the characteristics of those intermolecular forces. So stronger intermolecular forces cause substances to melt and boil at higher temperature because the molecules stick together better and don't separate as easily. So the Coulombic forces are better able to overcome the kinetic energy forces that are trying to break them apart. Hydrogen bonds are the strongest intermolecular forces, and only nitrogen, oxygen, and fluorine can hydrogen bond. So look at the light blue line there. You'll notice the boiling point. It measures the boiling point on the vertical axis and the molecular weight on the horizontal axis. And the one boiling point you recognize right away is water. H2O boils at 100 degrees centigrade. So water has a much higher boiling point than H2S, H2SE, or H2TE, the light blue line. Now, what's the significance of those other three? If you look at them, they are all 2 hydrogen atoms bonded to elements that are in the same group as oxygen. So that's the 6A group on the periodic table. So that would be oxygen. Below it is sulfur. Below it is selenium. Below it is tellurium. So they all have 6 valence electrons, just like oxygen, 2 of which can bond hydrogen. So they can all form H2 type compounds. So H2O has a much higher boiling point than H2S, H2SE, or H2TE, the light blue line, because it is the only compound that has hydrogen bonds. S, Se, and Te cannot form hydrogen bonds. So that explains why water has a much higher boiling point. And that's the type of question they could ask you on the AP exam. Why does water have a much higher? It's the only one that has hydrogen bonds. The other 3 molecules are polar molecules, so they will have, if you put them in just a pure substance of H2S, for example, if you put H2S in just H2S, they will have dipole-dipole bonds because they are polar molecules. H2SE is polar, H2TE is polar, so they will dipole-dipole bond, but that's not as strong as a hydrogen bond. Now, let's look at the next line, the red line. Hydrogen fluoride, HF, has a higher boiling point than HCl. And all of those, by the way, are, as you're going to learn in the course a little later on, are acids. HCl, HBr, and HI are strong acids, and we'll learn the definition of that later. HF is not a strong acid, but it does have the highest boiling point of those 4 compounds. So HF has a higher boiling point than HCl, HBr, or HI because fluorine can form hydrogen bonds, whereas the other molecules can only form weaker dipole-dipole bonds. So stronger intermolecular forces cause substances to melt and boil at higher temperatures because the molecules stick together better and don't separate easily. NH3 has a higher boiling point than PH3, ASH3, or SBH3 because NH3 hydrogen bonds while the others don't. Again, oxygen, fluorine, nitrogen are the 3 that can hydrogen bond because they have a high enough electronegativity to pull the electrons towards the central atom, either oxygen, fluorine, or nitrogen, and away from the hydrogen. And that means the proton of the hydrogen, the nucleus of the hydrogen, which is just a proton, tends to stick out more. It becomes more exposed. And so it can go over and bond with the lone pair on another atom that's also a central atom of oxygen, fluorine, or nitrogen. Again, go back to the first lesson and review hydrogen bonds, or come talk to me if you still don't understand that. Now, one thing we notice, we're now down on the light green line. One thing we notice is that the molecular weight goes up, then the boiling point goes up. And that's because molecular weights have more electrons. They bond more strongly, a little bit more strongly than lighter elements. So So heavier molecular weights bond more strongly than lighter elements. All right, now at the bottom line, the bottom line has CH4, and then it's all the way to SNH4, and the bottom line from CH4 to SNH4 contain nonpolar molecules. And you're going to learn by looking at those chemical formulas why they're nonpolar. We'll talk about that in a few weeks. But they contain nonpolar molecules that have only London dispersion forces, LDF. Those are the weakest type of bonds. LDF are stronger with larger molecules because they have more electrons. So SNH4 has more electrons than CH4. So when you're talking about nonpolar molecules, they tend to have weaker intermolecular forces. The only ones they have are London dispersion forces. So you'll notice the light blue line is down below the other three lines. However, you'll notice that one of them, SNH4, has a higher boiling point than, say, pH3. So if you have a large enough molecule, then the London dispersion forces can bond pretty strongly. And again, go back to lesson 1 and listen to the part on London dispersion forces, and that will explain that you can actually have some pretty strong bonds with London dispersion forces, but they are considered to be the weakest of the 4 types of intermolecular forces. Okay, phase diagram. You should be familiar with this. They generally, I'm told, don't expressly test on this, and I've not heard of a question on this. It's considered to be prior knowledge. You're supposed to know about phase diagrams from previous chemistry classes, but for many of you, this is your previous chemistry class. So what a phase diagram is, it kind of has that Y-shaped curve, and it shows at what temperature and pressure the 3 phases of matter of a particular substance will be. So phase diagrams are unique to the substance. Water has a different phase diagram than carbon dioxide, which has a different phase diagram than anything that you can think of, methane, for example. So the 3 states of matter are solid, liquid, and gas. A phase diagram shows the state of a substance at a combination of temperature and pressure. The names given to phase changes are shown in the phase diagram. So let's remember what that relationship was. It was on about the second or third slide of the first lesson of this unit. That pressure and temperature combine to determine whether something's going to be solid, liquid, or gas. So higher temperature, that one's kind of obvious. The higher the temperature becomes, the more the substance moves from solid, like just think of ice, always think of water in this example, to liquid water, to gas, to steam or vapor. So that's with higher temperature. Higher pressure generally goes in the opposite direction, because remember what we said back in the first lesson. Pressure basically squeezes the molecules together. So if you have a gas and you start increasing the pressure, you're going to squeeze the gas molecules tighter and tighter together until they eventually become a liquid. And then if you squeeze them together even tighter and tighter with higher and higher pressure, they'll go to becoming a solid. You'll just by brute force squeeze the molecules into being a solid. So higher pressure will generally produce solids, whereas higher temperatures, it'll tend to make things go from gas to liquid to solid. You'll go in the direction of solids, whereas higher temperature will make things go in the direction of gases. You'll go from solid to liquid to gas. And so you can kind of see that if you study this phase diagram. So the terms that you should know in connection with the phase diagram, let's go over those. Let's start with solid to liquid. Those are the easy ones. Those are the ones you've used all your life. So think of solid water, which is ice, going to a liquid. We call that melting. And when liquid water goes to a solid ice, we call that freezing. Okay, now go over to liquid and gas. When a liquid vaporizes, when it goes into steam or evaporates, we call that vaporization. When you go in the other direction from a gas, so like from the mist that's out at nighttime, then early in the morning you see water on everyone's windshield of their cars, or you see it on the leaves, that's called condensation. So the molecules come together. So that's going from gas to liquid. And then the two that are unusual, and you rarely see them, but we'll show you a quick demonstration of carbon dioxide, and that would be what's called dry ice. If you go from a solid directly to a gas without going through a liquid phase, that's called sublimation. That's what dry ice does, and I'll bring in some dry ice and you can see that firsthand. If you go in the other direction from a gas back to a solid without going through the liquid phase down there in the lower left, that's called deposition. Now, there is a pressure and temperature for every substance where it's right on the borderline of all three states. If you move a little bit in any direction, you'll either go to a solid or you'll go to a liquid or you go to a gas, just by a slight change of either pressure or temperature. So you can think of it as existing at all three states at the same time, or it's just kind of this middle ground, and that's called the triple point. And you can see that down there kind of in the lower left side of the graph. Now, as you increase temperature and pressure, those are going to work against each other. And as you get to very high temperatures and very high pressures, the temperatures are going to want to add kinetic energy and break the molecules apart into gases, whereas the pressure is going to want to squeeze them together and move them back towards being liquids or solids. So the pressure and temperature, as they both get very, very high, are fighting against each other. So you finally get to a point called the critical point, and that's the temperature above which it can't exist in any particular state. Okay, so it's kind of existing as both a liquid and a gas. All right, so let's look at a couple of specific examples. For all substances, if we hold the temperature constant, and so we'll just call it T2, you see it down there on the bottom axis, and increase the pressure from C to D, the substance will condense from a gas to a liquid. So that makes sense. It has a certain amount of kinetic energy, but now you're squeezing it more and more as you go from C to D. You're increasing the pressure on it, so you're squeezing that vapor down into a liquid. So that's what going from C to D represents at T2. Now let's look at T1. For most substances, if we hold the temperature at T1, and let's say we start at point A, and we increase the pressure from A to B, the substance will freeze from liquid to solid. So again, the temperature staying the same, it has the same amount of kinetic energy, but again, the pressure is increasing as you go up from A to B, so you're squeezing the molecules of liquid even tighter together, and that causes them to become a solid. They just get stuck together, they can't move around anymore at point B, and they become a solid. So higher pressure squeezes molecules into a tighter position and creates a solid. The critical point of a phase diagram is the pressure and temperature at which the gas and liquid phases cannot be distinguished from each other. And that's, it says point D, but it's actually, it's where it says critical point. Critical temperature is the highest temperature at which a liquid can exist. The triple point A is the pressure and temperature at which the substance exists as a liquid, solid, liquid, and gas at the same time. So we've talked about that before. Molecules with high intermolecular forces are either highly polar or they're large nonpolar, that is large London dispersion force molecules. Those are the molecules with high IMF. They stick together better, so they have higher critical temperatures than smaller nonpolar molecules. So, highly polar and large nonpolar have higher boiling points than weaker polar and smaller nonpolar. Compare the phase diagrams for water and carbon dioxide. At normal room temperature, about 300 degrees Kelvin, that's a little bit on the warm side, but it's fairly normal room temperature, and pressure of 1 atmosphere, shown as point X, water is a liquid and carbon dioxide is a gas. So over on the right is water, and you can see the heavy red line is 1 atmosphere of pressure, And if you see where the X is, it's right above about 300 degrees on the temperature axis down on the bottom. So that would be normal room temperature and pressure. And you can see that X is clearly in the liquid range for water. At normal room temperature, water is a liquid. If you look at carbon dioxide, it has a similarly shaped phase diagram, but you can see the liquid phase is much, much smaller. The gas and solid phases are much, much bigger. And you can see that the heavy red line again over on the left side where it says carbon dioxide is at 1 atmosphere of pressure, and it's roughly above 300 degrees Kelvin. And that would put carbon dioxide in the gas region of the phase diagram. And as we know, carbon dioxide, which is what we exhale every time we breathe, is a gas at normal room temperature and pressure. All right, structure and density of water. Now, water is unique in many, many ways. It may seem like not a very interesting substance in everyday life. It's kind of just there. But in chemistry, it has some amazing properties, and you're going to learn one of them here. Solid water ice molecules are held farther apart by hydrogen bonds. Liquid water molecules are freer to move around and stay closer together. This means ice is less dense than water. So what density is it's how much mass, or you can simply think of it as how many water molecules you have in a given amount of space, in a given amount of volume. So what hydrogen bonding does, if you look at the ice over there on the left, is it causes the water molecules to form these nice, pretty crystalline structures. You'll see what that looks like in a few slides. But basically, the hydrogen on one water molecule is attracted to the lone pair of another water molecule, and they kind of hold each other apart from each other because they're in a very specific geometry for them to hydrogen bond. If you look at the liquid water over on the right, you see that the water molecules are a little freer to move around. They can actually squeeze into spaces that they couldn't when they're hydrogen bonded. And so you can see that the liquid water is more densely packed. You have more water molecules in a certain amount of space than you do with ice, with solid water. That is a highly unusual property. Most substances, when they're in their liquid form, they have more energy. We know that. And so they move around more freely, and so they space apart from other molecules of their own type a little bit better. So they're less dense. When you start to freeze them or compress them down, it squeezes the molecules together. And so in solid form, when you put them under higher pressure or lower temperature, they start to come together closer and form a solid. So in almost every substance, the solid version of that substance is more dense because the molecules squeeze tighter together or can hold tighter together. So they're more dense. You have more molecules in a certain amount of space. For liquid water, it's the opposite. Liquid water, they're tighter together. They're able to fit together more tightly in liquid water than in solid water, and that's very unusual. And that has an incredibly important property. That is an incredibly important property that explains why we can have life on Earth. Without that property of water, which is very unique, we wouldn't be able to have life on Earth. Why? Because think about it. When water freezes on a lake, it turns to ice. It becomes less dense than liquid water. Whether something floats or sinks is determined by its density. So less dense water, which we call ice, solid water, less dense water floats on top of liquid water. For most substances, the solid form will be more dense than the liquid form, and it will sink. Think what would happen if water did that. If water froze to ice on a lake and became more dense, it would sink in liquid water, and then what would happen? It would go down, it would settle on the bottom, it would kill all the plant life on the bottom of the lake. More water on top would freeze. It would become more dense. It would sink. And eventually the entire lake from top to bottom would freeze. All the fish would be killed. All the plant life would be killed. As we know, in the wintertime, when a lake freezes is it only freezes on the top because the ice floats. So the fish can continue to live down below, the plant life can continue to live down below. If that wasn't possible, all of our oceans would be dead. So the fact that water has this unique property that in solid form ice, it's less dense, and therefore it floats on top of liquid water, is what allows there to be life on Earth. So solid water molecules form a hexagonal structure where there's a lot of space between molecules. This makes ice less dense than liquid water. So you can see it's a nice, pretty crystalline structure. Hexagonal means 6 sides, and that's how water molecules form when they're solidly hydrogen bonded together. And I think this is maybe even a little better diagram. Stronger intermolecular forces cause substances to melt and boil at higher temperatures because molecules stick together better and don't separate easily. Okay, but anyway, the diagram down there shows water vapor, that's steam. The molecules are separated. It shows liquid water, and you can see how the molecules are kind of crawling all over each other and all around each other there. They're kind of closely packed together. And then you see ice over on the right where it's a nice, pretty hexagonal structure, but you can see how spread out the water molecules are. They're far less dense. There's fewer molecules in a certain area than in the form of liquid water, and therefore ice floats on top of liquid water. And again, to emphasize, that's very unusual. Most substances, it's the other way around. The molecules pack tighter together in solid form than in their liquid form, and therefore the solid will sink in its own liquid. A solid will sink in its own liquid. All right, here's another phase diagram. So now, this could be an AP question. Water has, because of that property, that unusual property, water has a slightly unusual phase diagram. And the unusual part is the line between where it says water and ice. That black line between where it says water and ice, where that red arrow is pointing to, that's unusual. That's a backward sloping line of the phase diagram. For most substances, the line will slope forward. It will slope to the right, so towards your right hand. Here it's sloping backwards towards your left hand. So why is that significant, and what does that have to do with the density of solid water, ice, being able to float on top of liquid water? Well, let's look at this. If the temperature is held at T1 and the pressure is increased from A to B, then water will go from a solid to a liquid. Remember the one we showed earlier where we increased the pressure at the same temperature? It went from a liquid to a solid because the molecules were squeezed tightly together. But here we have a fixed temperature, so we're not going to increase or decrease the amount of kinetic energy, and we're starting at point A. And so what's happening is the ice at point A is hydrogen bonding. So the water molecules are pushing themselves apart from each other and creating that pretty hexagonal structure that you saw in the previous slides. So it's less dense. So when the pressure is lower, ice can form. But what happens when you increase the pressure? You go from A to B. You start to push those water molecules together harder and harder. They can't have that nice, pretty hexagonal structure that collapses, and they're forced into becoming liquid water molecules where they're closer together and they can be pushed around each other. So that's what the backward sloping phase diagram here means. It's a little hard to understand the first time you hear it. Think about it. So down there at A, you have that pretty hexagonal structure where the water molecules are kind of spaced out in hexagons and they look really nice. Okay, that's at a low pressure, and that's solid water at a certain temperature, assuming that we're below the freezing point of the water. When you increase the pressure, you take that pretty hexagonal structure and you crush it. You basically push the water molecules together so they can't form those nice hydrogen bond hexagons. And so what that is, we can go back and look at this. Whoops, that's where we want. So they go from ice over there where they're nice and pretty. The high pressure squeezes those molecules together and crushes that pretty structure into what you see in the center, liquid water. Okay, so therefore higher pressure is going to move the water, the H2O from solid, from ice, over to liquid. And so that's what you see on this phase diagram. At A, you're at solid water with those pretty hexagons. As you increase the pressure, you crush those hexagons and you make them look like liquid water, what you saw on the previous slide, up at B. So increasing the pressure makes the water go from solid to liquid, whereas with most substances, it'll squeeze the molecules tighter together and make it go from liquid to solid. So water's unusual, and the effect that has on the phase diagram is it makes that line that has the red arrow pointing to it go backwards, slope to the left. So let's read this again. If the temperature is held at T1 and the pressure is increased from A to B, then the water will go from solid to liquid. This is different from most other substances. High pressure pushes water molecules closer together. Liquid water molecules are closer together, so high pressure creates liquid. That should be water there. It creates liquid water. Low pressure allows the molecules to spread out and create hydrogen bonds, create those nice hexagonal structures. So low pressure creates solid water ice. That's assuming that the temperature is the same in both cases. Water has a backward sloping curve between solid ice and liquid water. This is very unusual, so you should be able to explain that. That could be an AP level question. Okay, so now we're going to look at just kind of a flow chart. This is called a flow chart of the different types of intermolecular forces. So interacting molecules and ions is your intermolecular forces. So first thing you ask is, are they ions? And we'll work over from right to left. So are ions involved? If the answer is yes, then are polar molecules and ions both present? If the answer is yes, then you have ion dipole forces. Again, think of water dissolving salt, sodium chloride. The sodium chloride are ions, positive sodium and negative chloride ions, and the water is a dipole molecule. That is, it has a positive end and a negative end to it. But the positive and negative ends of the water molecule are not as strong a charge as an actual ion, which is a full 1 plus or full 1 minus charge. So that would create an ion dipole force, example NaCl and H2O. If a polar molecule is not involved, then you're going to have ionic bonding. Okay, you're going to simply have one atom, a strong guy, pulling an electron away from a weak guy. So a nonmetal pulling an electron away from a metal, and you'll have ionic bonding. Okay, let's go in the other direction. So now we're back in the middle. Are ions involved? No. So now we ask, are polar molecules involved? And the answer is yes. If the answer is yes, you go down and then ask, are hydrogen atoms bonded to nitrogen, oxygen, or fluorine? If the answer to that is yes, then you have hydrogen bonding. So example, H2O, NH3, and HF will form hydrogen bonds. If the answer is no, that there's not nitrogen, oxygen, or fluorine involved, but they are polar molecules, then you'll have dipole forces. So H2S and CH3Cl would be examples of that. Finally, we go over to where it says, are polar molecules involved in the upper left? If the answer is no, then that means you don't have polar molecules, you only have nonpolar molecules. Then the only forces that will be in effect would be London dispersion forces, and that would be things like diatomic molecules like I2, or could be even O2 or H2, or CH4 methane. When the number of molecules leaving and re-entering the liquid is equal, they are said to be in dynamic equilibrium, and the pressure they create above the liquid is the vapor pressure. Vapor pressure exists when a liquid molecules gain enough kinetic energy to break free and exist in the atmosphere above the liquid, creating pressure. So molecules up above the liquid will create a pressure called a vapor pressure. If the liquid is in a closed container, then some of the vaporized molecules will return to the liquid. Since hot water has greater kinetic energy than cold water, hot water has greater vapor pressure. Substances with high vapor pressure evaporate faster than those with low vapor pressure. Substances that evaporate faster are said to be more volatile. Now, you often hear the word volatile to mean it's something that's explosive or will catch on fire. That's not what it means in the chemistry sense. It means that it will evaporate more easily. That's higher volatility means it will evaporate more easily. So let's look at a graph. You should be able to interpret this graph. So on the vertical axis on the left is the fraction of molecules. You could think of it as the percentage of molecules or the fraction of molecules. The lower axis, the horizontal axis, is the kinetic energy. It's basically how much heat you're putting in, how high the temperature is. So the graph shows the fraction of molecules at different kinetic energies. Now the dashed vertical line shows the minimum kinetic energy required to escape the liquid. So if they can get to the right of that dashed line, they'll have enough kinetic energy to evaporate, to go up above the liquid. So the pink lower curve shows a greater fraction of molecules to the right of the line and that have enough kinetic energy to become vapor. So the red line is at higher temperature. The blue line is at lower temperature. So lower temperature, fewer of the molecules or lower percentage or fraction of the molecules can get to the right of that dashed line. Whereas at a higher temperature, a greater fraction of the molecules or percentage can get to the right of that dashed line, and that's why you see more area under the pink curve to the right of the line than under the blue curve. So a higher fraction of molecules are able to escape the liquid. And so you should recognize what this is saying and know how to interpret it. Boiling point of a liquid occurs when vapor pressure equals the atmospheric pressure pushing on the surface of the liquid. Think about that. The kinetic energy in the molecules in the water if they can get high enough, want to push a water molecule up out of the water and into the atmosphere. But that's not just a function of how much temperature you put in the water, it's a function of how much is the atmosphere pushing down on the top of the water. At sea level, the atmosphere is pushing down with more force than at high elevations such as up in the mountains. So, the boiling point of a liquid occurs when the vapor pressure equals the atmospheric pressure pushing on the surface of the liquid. The normal boiling point is the boiling point of a liquid at 1 atmosphere pressure. In other words, right here at sea level. At sea level, water at 1 atmosphere pressure boils at 100 degrees centigrade. That's the number we're familiar with for boiling point of water. In cooking, the water holds heat which cooks foods. Above sea level, so let's say you're up in the mountains, say at 7,000 feet elevation, above sea level the pressure is less than 1 atmosphere. Why? Because you have fewer air molecules up high above the earth than you do right down on the surface of the earth. So the pressure is less than 1 atmosphere and the water boils at a lower temperature. This means that the food takes longer to cook. Why is that? So let's be sure we understand that. So as you put energy into the water molecules, they start to wiggle faster, they start to move around faster in the liquid. And they transfer that energy into the food that you're trying to cook. Let's just say you're boiling a hot dog. They transfer that energy into the hot dog. Now, if the air pressure is very low, then once you hit a certain temperature, like say 95 degrees, then the water molecules are going to start evaporating up in the mountains because there's low air pressure. So it only takes 95 degrees of temperature to get the water molecules to evaporate up out of the water. What that means is that the water molecules that are still down in the water trying to cook your hot dog aren't going to cook it as hot because they can't get as hot. Once they get hotter than 95, they're going to escape and go up into the atmosphere. Down at sea level, where the pressure is higher, the water molecules can't escape until they get to 100 degrees. That means the water molecules that are down in the liquid water hitting your hot dog, transferring energy into it, are 100 degrees, so they're hotter. And that's why a hot dog will cook faster at sea level than it will at elevation, where the temperature of the water can only get up to 95 degrees before the water starts to boil away. Okay, and that takes care of our second of 3 lessons on intermolecular forces. So in the first lesson, you learned the 4 different types of intermolecular forces. In this lesson, you learned really how that affects the pressure, the temperature, are relate to the intermolecular forces, and how to interpret different types of graphs, such as the phase diagram, to understand what's going on with intermolecular forces. Okay, we'll see you on the next lesson.